We will use the 180 ps fast edge pulse generator module to measure the length of this network cable. The principle of measurement is as follows. If this is a wire with an open end, send a pulse signal at the other end of the wire. The faster the rise time of the pulse signal, the better. The pulse signal travels in the wire. The signal will return because the other end is open. We can use an oscilloscope to measure the time difference between signals passing through this round trip. If we know the speed of the signal in the wire, we can use the following simple formula. Length is equal to speed times time. To calculate the length of this wire. In addition, we use an oscilloscope to measure the round trip time. So, divide this time by 2 to get the time of a single trip. The time of a single journey times the speed of signal propagation is equal to the length of this wire. The speed of signal propagation in the wire is this formula. The speed of signal propagation in the wire is multiplied by attenuation factor by the speed of light. The attenuation factor varies depending on the wire. For example, some network cables are 0.6F. However, once the wire type is determined, the attenuation factor is a fixed value. Therefore, the speed of light, multiplied by this attenuation factor is the propagation speed of this signal. That is the speed of signal propagation in the wire times the single time. Then we can calculate the length of this wire. This is a small module of fast edge pulse generator. Power it up with USB. It will send a square wave signal at this end. The rise time of this square wave signal is very fast. Only 180 picoseconds. Then we input this signal to the network cable. It will return when there is an open circuit on the network cable. We can calculate the length of the network cable. Use a T-type female adapter to connect the B and C adapter. Connect the network cable to this end. Input pulse signal from here. This end is connected to an oscilloscope. Now let's input a pulse signal to it. But no wires are connected. At this time, the oscilloscope observed a 50 kHz square wave signal. If the oscilloscope has a 10 ohm input impedance, the peak-to-peak value is about 600 mV. If the oscilloscope has a 50 ohm input impedance, the peak-to-peak value is about 300 mV. Now we connect the network cable to be measured. Then measure with an oscilloscope. Gradually amplify the signal. Notice that this is the moment when the signal is sent. This is the time when the signal returns. We need to measure this time difference. Then divide it by 2. It is the time of single journey of the signal in this wire. Open the cursor measurement function of the oscilloscope. Manually adjust to measure the time difference. You can see that x2 is now equal to 490 nanoseconds. This time difference is 490 nanoseconds. Divide 490 nanoseconds by 2 to get the time for a single trip. Let's calculate. Use this formula to calculate. L is the wire length. The speed of light is this value. The attenuation factor of this wire is 0.66. Then divide 490 nanoseconds by 2 to get the single trip time. Finally, the length of the conductor is 4847 m. The traverse I actually measured was 49 meters. The value deviates by about half a meter. Let's talk about it. How do you know the attenuation factor of this wire? You can find a known length of wire. For example, 1 meter or 10 meters. And then plug it into this formula. You will find, given the length, the speed of light. Then measure the time value with an oscilloscope. Put them all into the formula. Then we will find the attenuation factor. Use an oscilloscope to measure the time used for signal round-trip transmission of a wire of known length. You can calculate the attenuation factor. After knowing the attenuation factor, you can find the length of the wire of unknown length. So that's today's video. If you have friends who like this video, please help to like it. Comment forwarding bye bye.